Good. So let's get started. I mean, we are here for AutoML, so we thought it might be a good idea to have a rough landscape of what AutoML is all about. And this landscape has emerged into a relatively rugged and interesting area of research where we have basically a lot of things going on. And I will now start to guide you through this landscape together with Matthias later on. So first of all, what is AutoML at all? AutoML is basically a way of optimizing machine learning algorithms and customizing those algorithms to a task at hand. So the idea is that we get from a user a task consisting of a data set and a performance measure or anything other or any other different desires that the user might have, and we try to fit those needs. And we optimize for the perfect match between machine learning pipeline and the desires or demands. And here we have different subproblems involved. And the first one is hyperparameter optimization. Hyperparameter optimization has been done already for quite some time, where we basically just have a fixed machine learning algorithm. We get a data set, we are interested in a specific loss function, and then we try to optimize the hyperparameter values in a way that the performance measure is optimized for that data set. Here we also have different sub areas or extensions to this basic problem of hyperparameter optimization, which is not only optimizing for a single criterion, but instead for multiple criterions at a time. This has been covered also last year in the AutoML fall school. However, we will not have any hands-on this year. But still, it might be interesting to know that multiple objectives could be interesting at the same time. And what could that be? Well, we are not only interested in performance nowadays, but also in other sub-criteria like fairness or interpretability, explainability, which has been or has become very important to users nowadays, that they are trying to also embed or incorporate machine learning technology in products, which are then also taking action in normal day or normal life. Other than that, we also need to have some means or some approach to do this optimization. And there we are mostly dealing with Bayesian optimization or evolutionary algorithms. So let's zoom in here so that you can also read. The pictures are pretty smallish in the background, maybe. So what we have basically is that we might have different machine learning models, and then we are trying to build a surrogate model predicting the performances, and then leveraging this knowledge we have gathered so far from the observations in order to sample new candidates that are more promising, that are expected to yield an improvement. And with this, we basically fill in here two main ingredients for Bayesian optimization: the surrogate model that covers the experience of the optimization process so far, and then also the acquisition function that is meant to trade off exploration versus exploitation, so that we basically have a common goal where to get or where to look at whether we want to be more risky and try solution candidates that are expected to yield some performance, but maybe not, or whether we would like to really locally exploit performances and then go for the last bit of performance here. Another means is evolutionary algorithms, where we are dealing with a population-based approach. So we have multiple solution candidates in parallel and try to use some targeted random search to get somewhere which is more promising to us. And by selection, mutation, and recommendation, we try to shape the population we have of solution candidates and push them into a direction where we are interested. Further alternatives are grid search, random search. However, as an AutoML community, we recommend mostly not to use them due to inefficiency. Other means are reinforcement learning or also planning, what MLPlan is doing. And there you can basically do a tree search, for example, in order to refine parameter. And here we will have some invited talk and a hands-on session on that. So first of all, we will have hopefully, an invited talk by Haitham Bouarma on Bayesian optimization, and then also by Caroline and Alex, who is yet to come, a hands-on tutorial using how to use SMAG, a Bayesian optimization tool. All right. So the one thing is that we would like to basically search for candidates that are performing well and sample candidates in a proper manner. But the other way how we could gain efficiency during AutoML search is to speed up the evaluation of single solution candidates. And here the community has come up with various things. Yeah? So first of all, we could use meta learning in order to collect experiences of past AutoML runs and transfer them to new problems, which is then on the left side. So we run AutoML multiple times, gather data, gather experiences, and then we try to predict, for example, runtimes of machine learning algorithms or performances of machine learning algorithms for new data sets, and thereby try to improve efficiency. Another thing would be also to have learning curves involved here, that we try to anticipate how learning curves will shape and evolve if we feed in more data. So we could basically start with small data portions in the training process, observe the behavior of the learning algorithm, and then try to anticipate when the learning curve will converge and at what point. As soon as one learning curve is dominated by any other learning curve, we can also already discard it. And speaking about discarding solutions, this is a very typical thing being done in successive halving or also hyperband, which is a very prominent hyperparameter optimization algorithm where we try to cut off unpromising solutions quite early. So imagine you have a certain budget parameter you can give in to evaluate machine learning algorithms or solution candidates. For neural networks, this might be the number of epochs which you can use. So the more epochs you give, the higher the performance probably, and the more costly the evaluation will be. And if you already observe in early epochs that this candidate is not worth it, you can already discard. And this is basically what successive halving is doing. It's just evaluating on minimum budgets, dropping away or discarding unpromising solutions, continuing with promising solutions, and then focusing more budget on those solutions that are also more promising. And in this regard, we will also have a hands-on tutorial here, so about meta learning by Joaquin Panchora. So regarding the first point on this slide. Already a small glimpse here what HPO packages might exist, at least in Python. So maybe this is already outdated, but here we have SMAG, which is, according to this table, the most promising solution, which is also why we would have a tutorial here on SMAG, of course. So wink. And with that, I would like to proceed with neural architecture search. Please don't quote me on anything I say about neural architecture search. I'm not an expert on neural architecture search, but I will do my best here to guide you through. So neural architecture search is basically a problem where we are focusing on a specific learning algorithm and model class. So as the name already suggests, neural networks. And here we can do basically interesting things. So we can search for different architectures, different compositions of neural networks, and find thereby architectures which are customized for a particular learning problem, and hopefully also then reach state-of-the-art performance, and being tailored here to a given task. And the main components of neural architecture search are the search space, the search strategy, and the performance estimation strategy. And in this regard, I will give you a few ideas of how that could look like now. And the first most related part about NAS literature is the search space of macro NAS, which is very familiar or very related to hyperparameter optimization, where we can have different hyperparameters to steer, for example, the width of the layers, the depth of the neural network, or just stacking multiple of such layers above each other. and also do some resolution scaling or compound scaling, where we try to increase the resolution of the single layers and thereby also increasing complexity of the neural networks. Why is it related to hyperparameter optimization? Well, we have a certain set of hyperparameters which take over this control, namely the width of the layers, the depth of the layers, and the resolution parameters, where we can just adapt the numbers and the network will extend or shrink accordingly. So yeah, this is basically directly related to hyperparameter optimization. But we can also do more interesting stuff. For example, cell-based neural architecture search, where we have different operations and we have different states we can reach. And then we can draw different connections between these states and basically form ResNet-like neural networks, where we have the input from other cells and yielding an output, which is then achieved via those max pools, skip connects, or convolutional layers here that are basically configured into a single cell. And then these cells are basically also adjusted in a certain architecture. And here you already have a lot of degrees of freedom where you can choose all these different connections here in order to get to the different states. And this already yields a very complex and difficult optimization problem. Another way of formalizing the search space is hierarchical neural architecture search, where we have different components we can use as building bricks and then combine them and inject them into each other so that we can get really complex neural architectures. And this, of course, also demands for a certain search strategy that can also cater for that. Yet another way of doing neural architecture search is by defining a so-called supernet, where we have different cells being arranged in an order, and then we can get there via different operations. So we have different states, and here we basically have different operations, so different layers or cells we can use in order to get to these states. And the cool thing about this is that we have on the left-hand side the supernet, which is the, defining the overall search space. And by selecting a subset of these edges, we can get a subnet, which is then also considered as a candidate, which is then also used for training. And what we do basically is to sample subnets, do a training step, and thereby fitting all the parameters together. So every solution candidate we will explore during the search will have an effect on the parameters of the supernet architecture, and thereby it's like a joint learning effort, which makes it more efficient because we are learning the parameters all together as long as we sample new candidates. Having spoken a lot about different search spaces we can consider in neural architecture search, be cautious on the step here. What we can also look at is how to speed up evaluation. And one very hot topic recently, or within the past 2-3 years, is zero-cost proxies for neural architecture search, where you try to estimate the performance of a neural architecture just by means of a single pass. However, over trivial baselines, such as estimating the performance according to the number of parameters or flops, this has no significant advantages so far. So if you're interested in doing research on that, this would still be the baseline here. And then we can even scale out. Yeah? So we've so far focused on just either doing hyperparameter optimization, adapting width and length or depth of the cells, or building the architectures as a whole. But we can also do something like deep learning here. Yeah? So deep learning pipelines are usually more complex than just having a neural network. We are doing imputation, we are doing a normalization and stuff. And this again yields a complex machine learning pipeline together with hyperparameters for the learning algorithm. Yeah, And then we can also combine these two problems again. And this basically yields then JAS or YAS, I don't know how to pronounce that, which means that joint architecture and hyperparameter search is combined. All right, a lot of model-based and theoretical stuff going on here, but in practice, all these evaluations are done on hardware. Yeah? And nowadays, we have different types of hardware being available, like GPUs, TPUs, CPUs, and also neuromorphic chips nowadays. This is why we will also have a hands-on tutorial on how to leverage neuromorphic architectures in order to gain some energy efficiency also in neural network training and maybe also in the future in neural architecture search. And we will have an invite to talk about neural architecture search also just today.
So Marcel mentioned meta-learning before briefly. So yeah, now we have started meta-learning. So we have seen neural architecture search and hyperparameter optimization. And we can do them very efficiently, but now we'd like to ask ourselves, hey, while doing this, we actually gather a lot of information about how a learning algorithm behaves. Could we maybe use that to actually do something? And basically, we could ask ourselves, can we learn something about the learning process? And this is then actually called meta-learning. And yeah, there are a bunch of different meta-learning things. Like the most common meta-learning technique is, for example, learning across tasks. We basically try to learn, for example, in Bayesian optimization, a model that can be used across tasks. But I don't want to talk too much about this, but briefly point out that actually we'll have a hands-on session by Joaquin, who just arrived. And yeah, so he's sitting over there. You can ask him things. It'll be on Thursday morning. But yeah, briefly, two, three things actually that I want to mention before moving on here. So the first thing that can be done is performance prediction. So one can actually predict performance of algorithms across data sets to try to actually select the best algorithm class, for example. Another very interesting and important thing is to actually learn about hyperparameter importance, hyperparameter effects. After doing a Bayesian optimization or some hyperparameter optimization, one can use hyperparameter importance methods. And in this case here we have a picture of using the Gaussian process to compute a partial dependency plot of how a hyperparameter, in this case the number of layers, affects the validation loss of the neural network. And on the right hand side, we have something that basically triggered a whole bunch of research on meta-learning. This is called MAML, Model Agnostic Meta-Learning, that was published in 2017. And it basically shows how one can train a neural network in a way that it can easily be adapted to different tasks. So basically, we want to train the network so that we can easily go to parameter 1, 2, or 3, depending on the different tasks that we're interested in. Somewhat similar to meta-learning and also sometimes falling into the realm of meta-learning is actually called a field called learning to learn, where our goal is to actually learn the learning process itself. So for example, one thing is one popular or prominent paper there was learning to learn by gradient descent, where people actually learn the gradient descent update rule by gradient descent. So basically they put another layer on top of the regular neural network to actually learn the update rule, and then could apply this update rule to different tasks. And yeah, the really nice thing is this is all gradient based and could be propagated from front to end. This was recently also extended into the realm of large language models by a tool called Opformer by the same folks, Yu-Tian Chen from DeepMind, and basically in the Opformer, also very cool thing is they basically learn with a language model to predict what is the hyperparameter setting to try to test. Yeah, pretty nice stuff. But besides learning to learn the learning algorithm, we can also try to learn directly something that is able to solve the tabular classification problem that we're interested in directly. And one such example that was like recently proposed is the so-called prior data fitted networks. And the idea here is that we have some, we want to learn to classify that given like the whole training data. So X train, the training matrix, Y train, all the neighbors of the training data, and X test the points we want to predict. Output like the probability of every class of every test point in a single forward class. Basically, this looks like this. You have like all these input points, and then at this point, we want to get the probability distribution. Sometimes also called in context learning. And basically, this thing that's basically a transformer architecture, pretty standard transformer architecture, pre-trained on millions of synthetic tabular data sets. And then if you have like encounter a real world task, you could just do one forward pass in order to get like this probability distribution. Now, this thing actually turns out to work in practice. We can get pretty good performance in less than 1 second. So basically, this thing was able to like perform on par for a few data sets to state-of-the-art AutoML tools, Auto2 and AutoML2, but basically at almost no time. So 1 second, it took this thing to actually predict something, while the AutoML tools took about an hour. That's a small caveat, otherwise everyone would use this. This thing only so far works for around 1,000 data points. So I think actually this number could be increased a bit too. I think around 4,000 is what they show in the latest version of the paper. But basically, you can also learn to actually like solve small classification problems with learning to learn or meta learning approach, which is pretty neat. And what's also pretty neat is that we'll have a hands-on tutorial about this on, I think, Wednesday afternoon. Samuel Muller, who is one of the authors of the tab PFN, will be around and show you how to actually like train your own PFNs about the abstract. Now we have all these pre-trained models right now, but there's also like we have like all these LLMs that have been like published in the recent time, like in the last year or so. Basically, last fall school we didn't have ChatGPT, we didn't have these GPT models really around. Then I think November last year they were released, and since then quite a few things have happened, and you can like use these new models for actually like AutoML, and you can also try the other way around to use AutoML to train these models better. And you could use AutoML, for example, to help with pre-training, fine-tuning, alignment training probably. On the other hand, you can ask yourself, these things can, like given a string or given some input, give you some string output, text output. You can ask yourself, hey, what can we actually do with this text output? And people have so far, for example, shown, hey, we can actually use this to, for example, suggest new neural architectures and use these things actually for neural architecture search. And also for data science. And I want to go any further into this topic because we'll have Marius and Alexander, who is still about to join us in the evening, give an overview of this topic, which I'm really looking forward to. And we'll also have one practical session on one data science or like one application of using GPT-4 for actually like helping with feature engineering, and that's called Cafe. It will also be conducted by Sam, who will join us tomorrow, I think. All right. With that, we can have like all these kind of different AutoML techniques. But now we have trained all these AutoML methods. How do we put them in practice? And one thing how to put them in practice was, for example, using some so-called AutoML systems. And these were really like the first things that happened in AutoML, I think, yeah, 2015, that's like 8 years ago. So basically like 9 years ago, AutoML was mostly about like building AutoML systems that take all kind of machine learning algorithms in one machine learning library. For example, here in this case, scikit-learn. The predecessor of that was called AutoVector. For those of you who remember, that was a Java software called Vector that was pretty well used in well, 2 decades ago, I think. And so what AutoScaler tried to do is basically like help people to not have to think how to build their scikit-learn models. And it would basically like have an interface, you give it like the training data, it would train the machine learning model for you. You wouldn't have to worry about which classifier to choose, what type of run to choose. This is basically like the first, I think one of the first success stories of AutoML. So how did this thing work? What does it do for you? We have the data set that we put in, and then some meta-learning steps. So one could think, hey, we just searched the whole space of AutoML methods, but actually one wants to use some clever meta-learning here as well. So you might by now see that meta-learning is a recurring trend here. So we have some meta-training data sets, so we actually pre-train, well, not a network here, but we actually learn a portfolio of what methods would work well in general on new data sets, on a few metadata sets, and then for a new data set, we would actually like then use this portfolio to actually warm start a global optimization, in this case Bayesian optimization algorithm, to actually tune a scikit-learn pipeline for us. This picture here is actually from AutoScaler 2. So in AutoScaler 2, it would actually also predict how to evaluate your model, so whether to use holdout or cross-validation, so that you actually also don't have to choose that yourself, which is also pretty handy in case if you have small data sets, you want to like use cross-validation, large data sets, you want to use holdout, and it basically like based on your time budget tries to figure that out for you, so you don't have to do it yourself. Then, as I mentioned, we have like the training and validation. And so basically training configurations one after the other, validating them on a validation set. And then in the end, instead of picking a single best model, we actually then build an ensemble. So one thing that's also pretty common right now, or these days in AutoML, is if you train a bunch of models, you don't like throw them away in the end and just pick the single best one. Basically take the best models and put them together in an ensemble, because that even boosts your performance even further at minimal cost. So yeah, imagine if you trained like AutoML or machine learning pipelines for a few hours, then spending another minute on building an ensemble is actually very little investment. That's still going to improve your model quite a bit. So the nice thing here is we've shown this for AutoScaler 1 and 2 in 2015 and 2022. This was also shown to also work for other pipelines, in this case for PyTorch models. So you can basically apply the same methodology not only for like conventional machine learning pipelines, but also for deep learning pipelines. Basically get also really strong performance in there. And we used to have AutoScaler tutorials at the last 2 fall schools, but this year we'll actually have something new. We basically figured at one point, hey, if you want to like build AutoML tools, you basically have to write a lot of the code over and over again. So we started working on something that helps us in order to like build AutoML systems more easily. This is called the AutoML toolkit. It'll make its first appearance during the fall school now here. And there will be a hands-on by Eddie on Wednesday morning. All right. So yeah, I've shown you this before. This is basically what AutoScaler does. You build one level of models down here. You input data, you build the models, and you do the prediction step. So that is one paradigm on how to do this. You do HPO. And there was another paradigm that was recently, like 2-3 years, like started out, which was popularized by a tool called AutoGluon, which is basically a very good implementation of multi-layer stacking. And what they do is they say we ditch hyperparameter optimization completely, but we rather invest all our time into evaluating every model as good as possible. And then afterwards, we're just gonna do stacking and do another bunch of models, and then only like so how does this look? We have the input, we have like a bunch of models. These are in this case hand-drafted model configurations. So using like the latest machine learning algorithms. I think when they started was like CatBoost, LightGBM, XGBoost, I think fast AI neural networks, and 2-3 more. You would basically train everything in a repeated cross-validation fashion, make some predictions, and then use these predictions in order to like increase the amount of information in your training data so you can the actual data with the model predictions. And then you train the models again. And then you basically have these models on the second level can correct errors from the first model level. They can also take additional information into account that the models on the first level created. So in order to boost the performance even further. And yeah, that's so far only a teaser. I don't want to go into much more detail because we have one of the folks from the AutoFluent team here, Alexander Schur, who will give a hands-on on how to use AutoFluent and how AutoFluent works, also on Wednesday morning. So with this, we have now basically seen meta learning, we have seen AutoML systems. Now the question is how do we put AutoML into practice? We have this nice slide here called AutoML Ops. So in order to run AutoML, you need to do a few things still, unfortunately. Or you still have a few choices, fortunately. You can see it however you want. So the first thing is actually, and I think this is really key, and this is what once AutoML systems are out there, people must be trained much more to actually get right, is actually understand the machine learning problem and set up the machine learning problem in the right way. So determine your objective, your metrics, and your constraints. So basically, once we have freed everyone from having to train or like tune the machine learning models themselves, people should really like take the time that is then given to them by not having to like run scikit-learn stuff themselves and invest it and understand the problem, understand the domain, know what we're actually optimizing for, what we actually want to achieve. This basically also means like is choosing like the metric, is the metric actually like optimizing what the business is actually looking for. Second thing is then design your configuration space. Depending on the method you're using, if you're using AutoFluent or AutoSQLearn, you don't need to do this. But sometimes you actually might want to like choose and design the configuration space for your needs to actually like include methods that are important for the problem you're tackling. For example, I think for problems like survival analysis or something, there is no AutoML toolkit around there yet, so you'd have to do that yourself. So you design the configuration space with the things you want in there, and then you can actually like run the AutoML system. And for that, you'd also then have to like choose like what HPO algorithm you use. So actually, since I now said there's no real survival analysis, you could then actually use the tools, the HPO tools we show you, and the AutoML toolkit we show you to actually maybe try to build such a tool. And then you choose your AutoML approach, and then you're almost good to go. Once you still need to figure out how much time can I actually allocate or allot for the whole thingy. That's also another important thing. Usually people have like, I don't know, 3 budgets that are very often used. Like one budget is like, you start the thing on Friday and come back on Monday. So you want the whole thing to run for like 48 or 60 hours or something, or you have the weekend. The other thing that people often like is like 1 hour and then they go for lunch. Or like, I don't know, like something like 12, 14 hours, and then it's like you start in the evening when you leave, and then in the morning you can analyze the results again, tune like your data over the day, and then restart again. So that's basically determine your budgets, determine how much you can actually spend, when you can spend it. And then the final thing is actually like you need to figure out like what's the AutoML system doing. I think that's also a very important aspect that we also need to actually get better on. More than in a second. So we briefly talked about metrics before. I think Marcel already mentioned a few, but since it was on the slide before, I also want to mention 1 or 2. So usually the first thing that people usually care about is something like accuracy. So it can also be one score area on a curve, but usually the first order of business is improving the performance. And so that's fine, that's good, that's in most cases actually like the first thing you actually need to show in order to like move further. But there's a lot of other things that actually would be very important practice. So let's assume that you actually like want to run your machine learning model on a different device. Let's say this ThinkPad here, or I'm pretty sure all of you have a smartphone and you can run machine learning models on smartphones too. But now people might have either like the latest iPhone or an iPhone from 3 years ago, and they're vastly different in terms of hardware capacity. And so one can actually really think about tailoring the machine learning models to the hardware to actually like use as few resources as possible to make the phone last, or the phone battery last as long as possible. That's something then, yeah, optimizing for energy consumption. If you have low memory, you want to optimize for memory consumption. Also inference time, to have real-time inference. So there's really a lot of things we can optimize for. And this is a really important topic. So one other objective we could optimize for is robustness. We have Margaret after lunch talking about NAS for robustness. You can optimize fairness. On Thursday, we'll have a session on AutoML and fairness. There will be a poster by a PhD student from our group actually on how to optimize jointly for interpretability and performance. And as we heard before, we'll have a session on neuromorphic computing, which is another architecture that you can tune for to get actually more efficient in terms of memory consumption, no, energy consumption, sorry. As I said before, we have like all these metrics, now we need to monitor them. There's, for example, one tool that has been developed in the group from Marius called DeepCave. And it allows you to actually like take, for example, the output of the SMAC toolkit that we'll show on Wednesday and basically get some nice visualizations on what is actually explored throughout the search. And it can also show you like the hyperparameter importance and give you like an overview of like what is your HPO algorithm actually doing, so that you can like while it's running actually get some ideas. So this is now on the how to run AutoML side. Now a lot of people of us here are actually also developing AutoML tools. Hope that a lot of you from the audience are also here because you also want to develop AutoML tools. And in order to do that, we need to experimentally validate that what we're doing is actually something useful. So a key thing and a key topic in AutoML research is actually experimentation. And that hasn't been covered too deeply yet, so I want to spend 1 or 2 slides on this topic. It's very often important to like compare, if you then have a new method to compare to like the competitors on really not one data set, not 2 or 3, like people in traditional machine learning papers usually do, but in order to draw some useful conclusions, like on 20 data sets or 50 or 70 data sets. So like to basically get some really good understanding and some valid performance measures in order to decide A is better or B is better. So now then you actually have to not only run every machine AutoML system once, but you have to actually run it repeatedly in order to also like get out some randomness. So in the end, it really boils down to running a few hundreds to a few thousand evaluations of the different methods that you compare to each other. And so in order to get this right, we need quite a bit of tooling there to help us there. So the first things that are important is, like I mentioned, we need a few data sets, like 20 to 70. Where do they come from? So you could now go to UCI and just like download all of them manually and like read them in, and then you'll figure out, hey, all these 4 data sets are in different formats. So actually the nice thing is there's other platforms, one of them being AutoML, which is a collaborative machine learning platform where people can store artifacts for and from machine learning research. And so one of the artifacts that is on there is data sets, for example. So you can really get like a lot of data sets there. I think right now it's at a few thousand on there. And the nice thing is they're all in the same format. So it's like one line of code to load a data set, and then you change the name and you get a different data set. You don't have to worry about the formatting at all. So now I said there's a few thousand data sets. How do you choose between them? So yeah, people have realized that this is an issue before. So actually we have defined some benchmarking suites, so collections of data sets that can then actually be used in order to conduct machine learning or automated machine learning on one specific problem domain. And actually, like going you one step further, this is the automated machine learning benchmark. This is a whole software tool that facilitates running AutoML tools on the datasets from OpenML in a fair manner, so that you can actually like fairly compare AutoML systems to each other, and actually like then afterwards figure out which one would be the best one, and also like if you develop yours, how you compare to the others, so that you can actually improve your AutoML system. Yeah, all right. So this will also actually be covered in the hands-on by 14. So I said before, meta learning is also learning across tasks. So these are a lot of tasks. So 14 is going to cover that in a bit more detail as well. And that's also like, so you see there Bishop et al. And also courses. So we can also talk to Bernd and me about these other tools, and we'll be happy to discuss with you. But I also said, hey, we're going to run a few hundred to a few thousand experiments. So we also need to somehow keep track of them. And yeah, we're not the first one who have to do this. So people also have come up with nice tools there. Put down like 4 Python tools and 1 tool in R. The great thing is we'll also have a hands-on session on these tools, because these can be really valuable if you have to deal with all these different experiments. So we'll have a hands-on session by Caro here in the front and Marcel, who you already have seen up here. And they will show you 2 tools that can hopefully facilitate experimentation for you. And with that, I want to briefly mention a few open challenges before closing or finishing my part of the talk. So one pretty obvious thing is like machine learning models are getting bigger and bigger. It's not only LLMs, but like any other model you want to have, like also vision models, they're just getting bigger and bigger. And like if it takes a week to train such a method on compute cluster, we cannot run a simple iterative algorithm that tries one configuration at a time, because that would take a year on a compute cluster. Or speaking differently, if it takes like 10 million to train a machine learning model, you cannot simply iteratively train one after the other, because if it takes like 50 iterations to train the whole thing, that'll be $500 million. I'm pretty sure we don't have access to that much compute anywhere. So that's one clear challenge, and that's important. And if someone actually moves forward there, that would be a huge success, not only for AutoML, but for machine learning in general. In a similar vein, actually, something that's also really like one of the grand challenges of AutoML is to actually find substantially novel architectures. People are using neural architecture search to improve neural architectures. And they were actually really successful in tailoring the architectures that exist to different hardware, to different needs, to different use cases or datasets. But like coming up with something substantially new is, I think, yet to be tackled. For example, something like the transformer, which was hand designed by, I think, a Mila intern in 2013. Something like that should actually then hopefully be discovered at some point by an AutoML. So then another thing is basically we said before, hey, these AutoML systems, they do the machine learning for the user. But so far, this also meant that they do the machine learning without the user. So the user sets these things up, then they run, and then they get back to the user and say, hey, I'm done. Here's the result. Please do something with it. So it would also be great to actually like put the human back in the loop, so that while the AutoML system is running, the human can actually interact with the AutoML system. For example, say, hey, I really think you should also try this configuration here. Or, hey, in a multi-objective setting, hey, I think you don't need to explore like the whole 2 objectives. I think I'm preferring if you go like into this direction and like only like have a look at a specific range of like one objective, for example, the runtime. Like you basically observe the whole system a bit, and while it's running, you actually like go in there and change what it's actually optimizing for, because you've already observed what you want. You've gained some idea of the direction where you want to go. The last thing I mentioned before So last thing, so I mentioned before that we have to run hundreds and thousands of experiments. This is really like requiring a lot of compute, and a lot of compute means that we actually need to spend a lot of like resources, and resources in this case meaning energy. As we all know that right now a lot of energy comes from not renewable resources, so we really need to cut down on like using these non-renewable resources. And that's why green AutoML, like using as few resources as possible to get good AutoML. And also when the AutoML is there, to have it use as few resources as possible is crucial to actually like move forward here. Yeah. I've mentioned that before. So last slide from my side here is then also like a brief overview of where we are right now. So here I've put down 5 circles with 5 different topics in machine learning, or that are around machine learning on there. So we have supervised learning here, and I think we're actually pretty good at supervised learning because like classification, like standard classification is one. Like really the first task that people usually tackle if they tackle any problem. So we're pretty good at that now. It also means like computer vision and so on is pretty well attacked with neural networks. But like if you go to these other fields, there's less and less. So in reinforcement learning, people are struggling with like a high amount of noise that's actually like in there. Like if you run like your agent on your environment, it's a highly noisy reward. But there's still a small field called AutoML that actually tries to tackle this. In recommender systems, I think the situation is even worse because like the issue is like your recommender system is then actually like the only thing you want to measure is actually like the recommender system interacting with the human. You usually don't have like a human to actually evaluate your recommender system. So you also have to come up with ways of like how to like automate recommender systems. Here's unsupervised learning, which is even harder because you don't have an objective to directly optimize for. And you can go even broader from machine learning to actually the full data science. So seeing this, you can basically see, hey, there's still a lot of ground to conquer and cover for AutoML. And those 4 things on the right-hand side, there's still so much that could be done to actually automate all these different things. I think, yeah, if you go home after this week and are looking for some things to do, you can start looking into these fields to get some, yeah, ideas.